All right, welcome to the second part of inhibition that we didn't get to on Monday. We'll just cover two more types of inhibition here. So we covered on Monday competitive inhibition, where we are binding at the same active site. So we're actively competing for the binding site with the substrate. The next type of inhibition we're going to talk about is uncompetitive. And here we have a binding constant, or inhibition constant rather. But the difference, and we're going to denote it with uncompetitive, is that it gets this little hyphen there. So for uncompetitive, when we talk about uncompetitive binding, we're going to bind to the enzyme substrate complex here. This is different than competitive, where we bind at the enzyme. Here we're binding to the complex. And what happens when an uncompetitive inhibitor binds is it binds away from the active site and it will distort the active site. So since the active site becomes distorted, the enzyme is no longer enzymatically active, or catalytically active rather, and you have an inhibited enzyme. So what does this do to Vmax and Km? Both Vmax and Km will decrease, because basically what's going on is this enzyme lowers the amount of enzyme. And so the maximum velocity will decrease, but the Vmax will also, or sorry, the Km will also decrease. It's a really interesting observation, because remember, Km means the amount of substrate to go 1/2 your maximum velocity. Well, if I'm lowering Km, that means it's easier to go to my maximum velocity. However, that's coupled with the fact that, Vmax is also decreasing. So you're actually going overall slower. So it makes sense that you need less substrate to go 1/2 this new, slower maximum speed. So let's see what happens to our Lineweaver-Burke. So the bottom here is cut off. On the x-axis, we have our normal Lineweaver-Burke, which is 1 over substrate. And remember, the x-intercept is minus, here it's minus alpha divided by Km. Remember, alpha is it goes with the amount of inhibitor we have, and it also goes with our inhibition constant. So alpha is the thing that's like our dial, right? That is what is lowering the Km in the Vmax. We're lowering by this constant alpha. And so on a Lineweaver-Burke, the way you know that it is uncompetitive is that you get parallel lines, right? As shown here in our image, the bigger the alpha, and the bigger the alpha means the more you are inhibiting, we just get parallel lines because both Vmax and Km are decreased. So that's uncompetitive inhibition. Let's go to our last type of inhibition, called mixed, also sometimes called non-competitive. And mix is really interesting in that it will bind the enzyme before it has substrate and in the enzyme substrate complex. And this is why it's called mixed, because it is a mix of the competitive and uncompetitive. So let me just rewrite what's missing here. We have our enzyme inhibitor complex and our enzyme substrate inhibitor complex right there. So that's what's below those arrows. Here, since we're mixed, we have both versions of our Ki. We have the competitive Ki and the uncompetitive Ki with our hyphen, because we are interacting with both forms of the enzyme. So we also have alpha and our alpha prime there. So we have both alpha constants. For our Lineweaver-Burke, Km can increase, decrease, or stay the same. It really depends on what our alpha and our alpha prime are, because both alpha and alpha prime will affect Km. So depending on what those variables are, our Km can increase, decrease, or stay the same. However, Vmax will always decrease because Vmax is only affected by alpha prime, right? Remember, competitive, which is alpha, does not affect Vmax. We can always outcompete our substrate. But uncompetitive does affect Vmax. Mixed is a mix between competitive and uncompetitive. Therefore, we only have one variable that's always going to affect our Vmax. Therefore, Vmax will always decrease. And what does our Lineweaver-Burke looks like? Well, Lineweaver-Burke, they will cross at a point that's not on an axis, right? So the way to tell mix is that if your lines are crossing not at an axis, you have mixed or non-competitive inhibition. Right. So what do you need to know from these series of slides? I would like you to know for our 3 types of inhibitors, how we affect Km and Vmax, how the Lineweaver-Burke looks like for all these inhibitors, and using our equations shown on this table, calculate alpha, Ki, or Ki prime. So make sure we go over that. And we're going to do a problem here. So I have an enzyme catalyzed reaction, and I add 5 nanomolar of an inhibitor, and my Vmax is 80% of my uninhibited value, while my Km is unchanged. So what type of inhibition is this? That has to be mixed, right? In competitive, Vmax doesn't change. In uncompetitive, both Vmax and Km decrease. So the only situation where Vmax can decrease while Km doesn't change is mixed. So next question. What proportion of the enzyme have molecules that are bound, right? So I'm going 80% my maximum speed. So let's say normally my Vmax is 100 molar per second. It doesn't matter what that number is. Well, I'm just randomly assigning a Vmax, and that is a valuable skill that's, hard to get. When can you know to assign a variable? Here, the reason I know is because I'm working in percentages. So my Vmax apparent is 80% of my maximum speed. Well, 80% of 100 is 80. So when I'm inhibited, I'm going 80 molar per second, right? And so to find what percentage are bound, you have to ask yourself, okay, if I'm going my maximum speed of 100, well, my uninhibited speed is 100. My apparent speed's 80. Well, what's the difference between those two? 20%. So basically all you have to do for that is look at what your maximum speed is and just do like 100% minus that. That's 20% are inhibited. All right. Let's do our inhibition constants now. So by inhibition constants, I mean alpha and alpha prime. So let's focus on alpha prime here. And let's look at all the equations we can use. Well, one equation to get alpha prime is Vmax apparent equals Vmax, Vmax divided by alpha prime. Or if I rearrange that, alpha prime equals Vmax divided by V apparent. I'm going to do some erasing. So remember, I randomly assigned V max and V max apparent already. So our alpha prime value, actually, sorry, this would just be alpha. This is not alpha prime. No, it is alpha prime. It is alpha prime. Second guessing myself. Alpha prime equals 100 divided by 80. Remember, I just randomly said Vmax is 100. So if I'm going 80% of that, my Vmax apparent has to be 80. So my alpha prime is 1.25. Right? So we have our alpha prime. Now let's solve for the Ki, which is Ki prime. So alpha prime equals 1 plus inhibitor divided by Ki prime, which is actually what's being shown down here. It's just cut off, because Zoom likes to cut off the bottom of my screen. All right, so let's put in some numbers. Alpha prime we just solved, 1.25 equals 1 plus inhibitor concentration, 5 nanomolar divided by Ki, which I don't know. But when you solve this, you should get 0.25 equals, well, 0.25 equals 5 divided by Ki, or Ki equals 5 divided by 0.25. Let me just do that really quick. My calculator. Divided by 0.25 equals 20. So our inhibition constant here is 20 nanomolar. That's Ki prime. So just a recap, the first thing I did was find alpha prime. And I did that by saying Vmax apparent equals Vmax divided by alpha prime. And the way I got that relationship is if we just go back here. Where is it? So here's the y-intercept for the Lineweaver-Burke, where it's alpha prime divided by Vmax. Remember, that's reciprocal, so we just need to flip it to get the relationship I just used. And it's also shown here. This is the better example. So this variable right here, Vmax divided by alpha prime, that is saying Vmax apparent. Right, so it's this variable right here that is showing us, oh, what is our Vmax apparent for this? So yeah, that's what we use to get alpha prime. And then once we had alpha prime, we could figure out our inhibition constant, which is Ki right there. And I gave you the concentration of inhibitor as well. Question 3. This is just figuring out the Lineweaver-Burke plots. And since it's very important to know what the bottom of this says, I'm just going to move this up here. Do some rearranging. Okay, so label the X and Y axis. So our X axis is 1 over substrate concentration. Our Y axis 1 over initial velocity. All right, so that's the X and Y axis. Now line A, the blue line, is regular enzyme and substrate. And I have a bunch of different lines here. I want to say, compared to line A, which line is showing competitive inhibition? So competitive inhibition, Vmax does not change. So we should all cross on the y-intercept. So line A goes for the y-intercept here. So I have 2 lines to choose from. for competitive, B or E. All right. And the next thing about competitive is that Km will increase. And remember, these are reciprocal axes. So if something increases, it's getting closer to 0. So E is getting closer to 0 while B is moving farther away. So the competitive inhibitor to A here is E. All right, next is our non-competitive inhibition. So non-competitive inhibition is that Vmax and Km will change. Vmax will go lower. So if something is going lower on a reciprocal plot, that means it's going further away from 0. It's really weird to think about reciprocal. It's just opposite. So if my number gets lower, I go further away from 0, right? So I have a couple of choices here. So remember our A line. So I have two choices, D and F, right? Now in non-competitive as well, Km can go higher, lower, or remain unchanged. We don't know. But what will always happen is that the lines will cross. So D does not cross A, so that's not it. So it has to be F. Next, uncompetitive, parallel lines. And we only have one line that's parallel to A here, and that's D. So E, F, and D. Last question, we can just ignore this. This is about making a plot. The idea behind this was you take that information, you make a Lineweaver-Burke plot. Obviously, I can't make you make a Lineweaver-Burke plot on the internet. So if you really want to understand how Lineweaver-Burkes work, this is a great problem for this, but I'm not going to ask you this on the test, on the final rather, so no need to know that. And I believe that's it. All right, so that's all you need to know, not too much more. Good luck studying for the final and all your finals. As always, let me know if you have questions, and good luck. Have a good rest of your 2020, everybody.